Hi, good day. Welcome to my talk on windmills of the minds and algorithm for Fermat's two squares theorem. My name is Heng Lan Chen from Australian National University. Today, there are 4 topics with an extra. The first one, sum of two squares. We start with the numbers 0, 1, 2, 3, etc. Given a number, there are 2 types, even and odd, and they occur by dividing the number n with 2. When the remainder is 0, we call it even, and when the remainder is 1, we call it odd. For an odd number, we can divide the odd number by 4, and there are 2 possible remainders, 1 and 3. They don't have names, so I give them names, tick and talk. The first 2 numbers, 0 and 1, are special. I call them bits for binary digits. 0 is special because of this theorem, and 1 is special because of another theorem. This symbol, the turnstile symbol, means that the theorem has been proved by a machine, or what we call formalized. Now we come to the primes. The primes are numbers that are not 0 or 1, and is only divisible by 1 or itself. Examples are 2, 3, 5, 7, etc. The only even prime is 2, which equals to 1 plus 1, a sum of 2 squares. How about the odd primes? There are 2 types of odd numbers, tick and talk, so there are tick primes and talk primes. 3 is a talk prime, 5 is a tick prime, etc. And as you can see from this example, a tick primes seem to be able to be expressed as a sum of 2 squares, like 5 equal to 1 plus 4, 17 equal to 1 plus 16. Still more examples. Now think, if an odd number n is a sum of 2 parts, then one part must be odd and another part must be even. If each part is a square, then there must be an odd square and an even square to form the sum. These examples shows that, or suggest that, this particular theorem, a tick prime is a sum of 2 squares, odd and even, in a unique way. And this is the mathematical expression of the theorem. And this symbol, as you remember, means that it has been formalized. My theorem prover is called HOL, which stands for higher order logic. This theorem actually comes from Fermat. He said that he had a proof, and he challenged others to offer a proof. Nearly 20 years later, no one came up with an offer, and so he gave a hint. This is very rare if you know about the legends of Fermat. Almost a century later, Euler took the hint and gave a proof. He had been working on and off for 7 years. Later on, other mathematicians, famous mathematicians, come up with their own proofs. Why? Basically because they found that the previous proofs are too complicated, and so they invented their own theories for their new proofs. There are more. This is another formulation of the 2-square theorem in a more precise way, all right, which says that if it is a prime, then a tick prime can be expressed uniquely as a sum of 2 squares odd and even, and only those tick primes can be expressed in such a way. G.H. Hardy, a famous number theorist, comment about this theorem. He says, this is Fermat's theorem, which is ranked very justly as one of the finest of arithmetic. Unfortunately, there is no proof within the comprehension of anybody but a very expert mathematician. He wrote that in 3 centuries later. Well, I am not an expert mathematician, so I don't know all the previous proofs. So what do I know? Well, I know the windmills and the mines. We try to recall what is a tick number. A tick number n, when divided by 4, gives us a remainder of 1. This is the way to express it in a mathematical way. The mod means remainder, but it actually means that number n is 1 more than a multiple of 4, which we can express in this way, n equal to 4k plus 1 for some value of k. Examples of tick numbers are these, by substituting the k with 1, 2, 3, 4, etc. Some of these are primes, some of them are not, and some of these are squares. How about a picture for a tick number? 37 is a tick number, and so we express it as 1 plus 4k, k being 9 in this case. The first one is equal to 1 times 1, and 9 is equal to 9 times 1. This can be given as a square, and 9 times 1 can be represented by 4 rectangles, like this, which forms a windmill. And by 9 times 1, I mean horizontal 9 and vertical 1. There is another picture for the same tick number, because when we write it as 1 plus 4 times 9, the 9 can be factorized as 1 times 9. Also for rectangles, but now in this form, right? Also a windmill, and by 1 times 9, I mean horizontal 1 and vertical 9. So a windmill is just a central square with 4 identical rectangular arms. And I shall use this expression, windmill x, y, z, representing x squared plus 4y times z. And these are the various forms of windmill, depending on the relative size of the values x, y, and z. I shall also denote a windmill x, y, z simply by triple x, y, z with 3 components. The value x is the size of the central square, y and z are the horizontal and vertical of the top arm, right? The one on top arm of the central square. And the 4 arms are arranged in a clockwise manner around the central square. And as we have seen, every tick number has at least 1 windmill, maybe more. Coming back to our example, the number 37 is tick number. How many windmills does it have? Recall that this is the expression for the windmill, and n is odd. So this must be, the other part is even, and so this part must be odd. And if the square is odd, then x itself must be odd. So we can compute this difference for all the odd x, right? Like this. So we arrange the odd x 1, 3, 5, 7 in a column, compute the differences, and then the difference will be equal to 4y, z, and we factorize the y and z to come up with the triple x, y, z, like this, okay? And for a large odd number, the difference will be negative, and that is when we can stop. When we collect all the windmills of a tick number, it will form its mills. So mills of 37 is a set of all the triples, and we'll count them. There are 7 of them, all right? And this is to denote the size or the number of elements of the set, which is an odd number. So this is the picture for the 7 windmills of the number 37, the tick number. Very soon we shall read their minds, okay? Given all the windmills of a number, we can relate them or pair them up by flipping, which means flipping the rectangular arm, say from 1 times 9 to 9 times 1. And so these two windmills will be related by flipping. The same for this one, 1 times 7 flip to 7 times 1. So these two triples will be related by flipping. And same for this one, 1 times 3 and 3 times 1. For the last one, as you can see, because the rectangular arm itself is a square, flipping is just itself, and we call this a fixed point. So flipping is a map, and it will take the triple x, y, z to x, z, y, right? Swapping the last two components. And if you flip once and then flip again, it just comes back to the original. And we call this an involution. The fixed point has this form, x, y, y, and this is an example. Whenever we have this kind of situation, a fixed point, then the number can be expressed like this, which becomes a sum of two squares. So a fixed point means expressing the number as a sum of two squares. Now, what is the mind? The mind is the biggest heart of the overall shape of the windmill. Like this, given a windmill, we can actually draw a little big square like this. And if we take this as the central square, it will become another windmill. So a windmill can transform to another windmill through the mind in red. We can take from left to right or from right to left. From left to right, we are going to expand the central square, but at the same time shrinking the arms. If we go from right to left, then we are shrinking the central square, but then we are going to extend the arms, okay? And if you take the side of the mind, which is a square, and use this expression for it, by simple geometry, we can express the mind in this particular form. Don't worry, what I want to show you is that there are three cases to express the mind, depending on the relative values of the numbers x, y, and z. In a similar way, we can pair the windmills up by like minds. Like this, these two windmills got the same mind, so we can pair them up. That means we can transform one windmill to another through the mind. These two got the same mind, so we can pair them up. These two also got the same mind, so we can pair them up similarly. For the very first one, because the mind is just the central square, is equal to the central square, so it just pairs up with itself. And so this is a fixed point of the map. I use the zigzag symbol for the map because it is first given by Sakia. And so it will transform a triple x, y, z to something else. What are they? We shall see in a minute. But if you take the second map, relating like minds, do it once and then do it twice, it comes back to itself. So this is also an evolution. A fixed point of this second map will be of this form, x, z, right? And this is an example. And this is a fixed point basically because in this case, the mind is just equal to the central square. So let us talk a bit about evolution. And evolution is a map taken into itself, like this, right? And a fixed point is a point x unchanged by the map. So if you transform a point x by the map, right, it just comes back to itself, and then this one is fixed. Flip is a simple involution, all right? And this is the expression as we have seen, just swapping the last two components. And we can prove it, formalize it. And a fixed point is of this form, x, y, y. And for a windmill, if you've got a fixed point, as I have said, then we can express it in this way as a sum of two squares. Seghers is actually devised by Don Seghers, and he get this expression without using the concept of windmill, which is quite remarkable. And this is the expression from Seghers. All right, don't worry. All you need to know is that it also got three cases, basically coming from the three cases of the mind. And it is an involution because if you do it twice, it comes back to the original, and we can formalize it. And the fixed point of Seghers is this form, x z, because the man is equal to the central square. For a Tic number, which has this form 4k plus 1, all right, then if you substitute this triple into the expression, it becomes like this. And if you equate it, right, then you have got this equality. And if this Tic number is a prime, then prime is only a trivial factorization. And so x must be 1. And then the conclusion is that 1k is the only fixed point of the second map. This is for a Tic prime. This is another way to look at the involution, right? It's just restate the definition. We are using some pictures. So this is a set, and there are some points, all right? And an involution will take a point, say this one to another one, but because doing twice itself, so this one must map back to this, and so pair things up. If you remember the diagram for the flip map and the second map, they have all these pairs. So pairing. This one pair with itself. All right, pair with itself. What about the last one? Well, the last one must pair up also with itself because every other one has been paired already, either to a different one or paired up with itself. These are called a fixed point of the involution. And for a finite set, we have this particular theorem, which basically says that because the involution have all this pairing, so this part will give us an even number of elements. So for the number of elements of the overall set, if that is odd, it must mean that there is an odd number of fixed points. And also, if there is an odd number of fixed points, then the overall number of elements of the set must be odd. And as a result, we can have some observations. And that is for any involution, if there's only one fixed point, then the size of the overall set must be odd. On the other hand, if the size of the overall set is odd, it must imply that there is at least one fixed point. Now, given a Tic prime, our previous slide shows that the second map has only one fixed point. And so it fits into this case, and therefore the number of windmills is odd. And because flip is another involution on the same map, on the same finite set, right, the flip fix must exist, and n can be expressed as a sum of two squares, right, because that one exists. So this is the basic idea behind this one sentence proof given by Don Seghers, right? And You have seen this before. And we call this a proof from a book because a mathematician refers to something called the book, in which God keeps the most elegant proofs of each mathematical theorem. If you look carefully at the second map, you can see that actually it just consists of addition, subtraction, and doubling. So there's no complex arithmetic. And so the implementation of this for computation is actually very simple: add, subtract, and double. What happened is that all these, even the windmills, been formalized in some other theorem provers. So what is new for me? This is the two-square algorithm. That means I'm going to find the two squares for the tick prime. And this is how the algorithm works. With the same tick number 37, you have all the 7 windmills. We start with the known Sega fixed point, the 11K, all right, and which is this one, the man equal to the central square. There are only two things we can play with. One is Sega and one is flip. This is Sega fixed, so there's no point in doing Sega once again, and so we flip it to a new windmill. And once we flip it, there's no point in flipping it back. So we use Sega map also to go to another new windmill. And so we repeat this process, flip and Sega, to get to other new windmills not encountered before. And do it once again, flip and Sega, then we arrive at the flip fixed point. And when we have the flip fixed point, we can extract the two squares for the number n. Okay, so we start from here, the non-Sega fixed, doing flip Sega, or what we call a composition of flip and Sega, and then we can arrive at the flip fixed point. For the code of the algorithm, we have the input, a tick number of this form 4k plus 1, and we want an output, a flip fixed point with this triple x, y, y, so that we can express n as a sum of two squares. On the left side is the flow chart. Basically, we start with this known Sega fix, and then check whether the last two components of the triple are equal, because if they are, we got the flip fixed point. If not, then we do the composition of flip and Sega, all right, to get from one triple to another, and we get looping back with the check at the very beginning. And this is the pseudocode, all right, expressing using the while loop. As we have seen, flip is simple, right? Just swapping the last two components. Sega is also simple because it only involves simple arithmetic, and therefore our algorithm is simple, and it actually is quite fast for tick primes, as long as the n is not too large. What we need to do later on is to prove that the code is correct, and actually this loop will terminate for a tick prime. Before that, let us see some sample run. In my theorem prover, I can use an evaluation, EVAL, once I have implemented the algorithm shown in the previous slide. And so I can evaluate the two square for 37, and it will give me a pair 1, 6, which means that 1 square plus 6 square is equal to 37. In the theorem prover, I can also prefix the whole command by time. Once I do that, it will give me the execution time of this evaluation. And for the number 37, it is very quick. Here are more examples. And for the number 97, it is still quite fast. For 97, it gives me the two squares, as, the two numbers as 9 and 4, which means that 9 squared 81 plus 4 squared 16 is equal to 97. This is a 10-digit number, and it takes about 2 minutes to get two squares. And this is an 11-digit number, and it takes longer. It takes 6 minutes to get the two squares. Okay. This execution, this evaluation actually is just using the symbolic arithmetic of the theorem prover. The theorem prover is designed for proving theorems, not for calculations like this. So it just uses symbolic arithmetic to do the evaluation. Symbolic arithmetic is orders of magnitude slower than native code, and so these results are quite impressive. For the correctness of the proof, we have to go to the orbits and puris. What do I mean by orbit? Well, let us use F to stand for the second map, G stands for the flip map, and as we have seen, both of these are involutions. And we are considering the composition, all right, F circle G, and I denote it by phi. This composition is actually a permutation, not an involution anymore, but just a bijection on a set. And we are going to apply this several times, apply the composition, all right, several times. And for a finite set, each iteration of this composition from any point must repeat. Like this diagram, all right? Say we start with this point, and the map phi will give us to another point. Another phi will give us another point, a different one possibly, and a different one. But because it's finite set, it cannot always be different if we keep on applying phi. And so eventually it will come and come back to the starting point. Now you may wonder, when it comes back, can it come back to a different point, like this picture, not at the very start, say here. So I put a question mark here. The answer is no, it can't do that, because the phi is actually a bijection, so it maps distinct points to distinct points. And therefore, if these 2 points are distinct, if these 2 points are distinct, then they cannot map to the same point. And so this is not allowed for a permutation. And so this cannot happen, and only this can happen. And so the repetition must occur at the start, forming what I call an orbit, all right, not this picture. Orbit here. The length of the orbit is called the period, all right, and the period is always bigger than 0. The iterations are written in this form: phi x for once, phi square x for doing twice, phi and phi. If you do it 3 times, then it is phi to the power 3. And by convention, we denote the very first one by phi to the power 0, where it is not changed. The key to the proof of the correctness of the algorithm is to consider orbits like this, but from one of the involution fixed points. Right? Phi is a permutation, but it consists of 2 involutions behind it. Let's see. This is just to make sure that we are on the same page. Phi is this composition of F and G. And we are going to consider an orbit of X, all right? And this orbit must have a period, and the period can be either even or odd. We shall consider two cases. If the period is 6, let us see the picture. All right. So we start with a point x here, and doing 1 we have a 5x. Doing twice we have a 5 squared x, and come to here. This is the 4th time, 5th time, and the 6th time. All right. And because it's a period, you come back to the starting point. And I use black dots for the actual destination for phi. But phi consists of f and g inside. So if you consider the f and g, which are involutions, then it is first g, then f. So first g, then f, first g, then f. And so there are some intermediate points. And I use a white circle for the intermediate points. Okay? So this is a picture for an orbit of phi with period 6. And if the orbit has an odd period, like 7, then this is the picture for it. The thing repeats after we apply phi 7 times. And the black ones are the real points which from phi. But there are intermediate points by the f, by the g and f. And I indicate the intermediate points by white circles. And what we are going to do is to get some special properties for the starting point. What happens when the starting point is a fixed point of either f or g? Let alpha be a fixed point of f, all right? And we shall consider an orbit with even period 6. So we take this picture, but then the very first point is a fixed point of f. So it goes back to itself. And so we try to trace what happens. First g, then f, this is once, twice, 3 times, 4 times, 5 times. And the last time, the 6th time, the g must actually go to here so that g and f will complete the orbit. Right? So g has to stretch to here. But if g is stretched to here, then you have 2 seemingly different points going to the same point, which, right, for an involution, which is a very special bijection, right, is really not allowed. So what this means actually is that these 2 points actually are equal because they actually will go to the same destination. And because of that, f is also an involution, all right? If these 2 points are the same, then they must come from the same point. And so these 2 points must be the same also. The same reasoning will tell us that these 2 points actually are the same. And likewise for these 2 points. And so for the very last pair, these 2 points, by the same reasoning, G and G here, they actually must be the same. And so we can clean up this picture by merging the intermediate points with the real points in this way, right? So now we eliminate the intermediate point and just take the real point. And so this one is merged to there. This one is merged to there, right? And so at the right-hand side, here we actually have another fixed point for f. So what we can observe from here is that for an orbit of from an f fixed point with even period, there must be another f fixed point at the halfway point. Okay. Let us have the alpha, a fixed point of f, but now in an orbit with an odd period 7. So we take this picture and f fixed point on the left. And we try to see what happens if we take the intermediate points. So the same reasoning last time. For the very last iteration, this f and g must go in such a manner so that when we apply g and then f, the f will come to a fixed point. And that means these 2 points actually must be, and so it has some implication for other points. Like this. These 2 points must be the same because they actually lead to the same point over here. And if these 2 points are the same, then these 2 points are the same, and these 2 points must be the same, etc. Likewise here. And so now these 2 points must be the same. And we do the clean up like the last time, merging the intermediate points to the real points. We get this picture, okay? And what we find is that we have a G fixed point, right? Not an F fixed point. This is an F fixed point. This is a G fixed point at the right-hand side. And so this tells us that for an orbit starting from an F fixed point, but with off period, there is a G fixed point at the halfway point. These are examples, but I have been able to put it as a theorem. The theorem says something like this. Let F and G be involutions, and FO circle G be the composition. Right. Then at the halfway point of any phi orbit from an F fixed point, if the period is even, there's another F fixed point, right, the halfway point. If the period is odd, then there is a G fixed point at the halfway point. Now, we call that a tick prime has this form, 4k plus 1. All right, and the set of windmills is finite. And we have F equal to Zagier map, G equal to Frit map, and they are involutions. And Zagier has only one fixed point because for a prime tick prime, it is only one fixed point, 1k. And because of that, the period cannot be even. Because if it's even, there must be another Zagier fixed point, but Zagier has only one fixed point. And so the period of the orbit of the composition from this Zagier fixed point must have an odd period. And because it has an odd period, at the halfway point of this orbit, the iteration must hit a fixed point. And the fixed point will give us the 2 squares, expressing the tick prime n as a sum of 2 squares. Thus, for a tick prime, the 2 square algorithm actually works. And I give it a tick. Okay. You can read my paper for the details of the proofs. All right, and there's a preprint of the paper at this location. Just to summarize, the proof depends on the permutation by composition of involutions and considering permutation orbits and periods. The orbits are the ones connecting one type of fixed point to another, and the situation will depend on whether the period of the orbit is odd or even. Now, this paper has been accepted by CPP 2022. CPP stands for Certified programs and proofs, right, which is a conference for theorem proving. And for the acceptance of the paper, it must go through the reviewers, and there are 3 reviews, right, for the paper. So let us look at the reviews by the various reviewers. For the reviewer number 1, he said that I'm not an expert on neither number theory nor HOL4. So the fact that I could follow the paper is proof that the exposition is very good. That's encouraging. And he said, my only concern with the paper is that this result has been formalized many times before. It would hence have been nice with a more thorough comparison with the other formalizations, both in terms of number of lines and also in the proof strategy that they formalize. And so I took those comments and add this information in the revised version of my paper. There was a second reviewer. He said that the paper is clear and easy to follow with many figures. Even if the proof already exists in other proof assistants, I think there is enough new material for it to be published. Also, very good comment. My main criticism is the title, Windmills of the Minds. It uses unfamiliar words in this context. For a non-native English speaker, this is frightening. I hesitated before bidding for this paper due to its title. Well, I wish I could introduce to this reviewer the following song and see if I can find it.
As the images unwind, like the circles that you find in the windmills of your mind.
So this is how the title of my paper comes from. For reviewer number 3, he said that I did not expect to write this paper, but in fact I did, and I advocate acceptance. Despite some comments to address, the paper is extremely well written, indeed beautiful. Moreover, there's something wonderful in taking a one-sentence but nearly incomprehensible proof and explaining the magic in a clear 12 pages. He raised these issues. The most serious issues are the following. How much of this explanation is novel? A thorough and careful discussion on related work? Is the algorithm better than others? So in my revised version, I include the answers to these questions. I said that for the first one, the ideas are taken from various authors. I use pictures to explain. For the second one, the staircase proof and windmills have been formalized in other theorem provers, but no algorithm or correctness proof has been given. And for the last one, I said that the algorithm is fast for not too large tick times. The algorithm is simple to implement and have been formalized to be correct. So this is very good. That's all for today. Thank you very much.